Okay, so what I want to discuss next are other key problems, central problems in the theory of random walks, and these have to do with returns to the origin. So a return to the origin is essentially equal to the event that at a certain time 2n the position of the random walk is at 0. Okay. Of course, this time can only be an even time, so I will going to be using 2n. So what is the probability of a return to the origin at time 2n that I will call P2n? Well, this is an easy question, because essentially for a random walk of 2n steps to go back to the origin, you have to have n steps up and n steps down. So out of the 2n steps, n of them have to be up and n of them have to be down. So the probability is just given by this. And now you can use the Stirling approximation of n factorial and find that for n large, the asymptotic behavior of this probability is given by 1 over square root pi times n. Okay, so this probability is non-zero, and it is going to 0 very, very slowly. Okay. Now, this concerns the probability that a random walk gets to the origin, the random walk is at the origin at a certain time, okay, that at this point there are, but what about the probability that this return to the origin is the first one? Okay, so what about the probability that the random walk returns to the origin at this time for the first time? Okay, so we call this first return to the origin. And it is the event that S2n is equal to 0, but that Sk is different from 0 for all k that are between 0 and 2n. Now you see that this is a rather more complicated event, because it involves not just a condition at time 2n, but a condition on all previous times. So we want that the random walk is at the origin at time 2n, but that it didn't go to the origin at any previous time. Okay. So we will call F2n the probability of that you have a first return at time equal to 2n. Okay. So you see by this that we can also write this as a probability distribution of a waiting time, which is the first return time. So we can also describe this as in terms of a waiting time. So from So we use the notation that for this is that for n equal to 0, we say that the probability of first return to the origin is equal to 0, because this is not considered as a return. And of course, by this equation here, you have that u0 is equal to 1. Okay? Now, these two probability distributions are related because, say, if you want to ask yourself what is the probability that you get a return at time 2n, then you can compute it in this way. So at some point you should get a first return at time 2 nu, and then after this you should have that the random walk is back at the origin after 2n minus 2 nu steps. So you can write this in this form. And then you can sum on all nu from 0 to n. And this will be true for any n positive. So the idea of this equation is, is that in order to go back to the origin, you must have come back to the origin for the first time at times 2 nu, and nu can be from 0 to n. And then you have to be back at the origin after 2n minus 2 nu steps. Okay, so this is a general equation that holds also for many other problems. So this idea that is behind this equation is more general. It applies to all events like the return to the origin that recur in time. So if you think of a sequence of events that recur in time, you can always think what is the probability that this event occurs at a particular time, and what is the probability that it occurs at a given time for the first time, okay? And these two probabilities will always be related by an equation of this type, okay? So, if you want to compute this probability, given that you know what is u2n, you can invert this equation here and compute f2 nu from this expression of u. Actually, we will find a simpler way to do this, which is based on the following result, which is a rather remarkable result. And this result is stated in Feller as a lemma. And it says that the probability that a random walk never goes back to the origin up to time 2n and including time 2n is equal to the probability that the random walk is at the origin at time 2n, which is equal to u to n, which is this one. Okay, so this is a rather remarkable result because it relates the probability of a very non-trivial event that involves all times between 0 and 2n to an event that only depends on what happens at the end time, at time 2n. So the proof of this statement is essentially based on the Ballot Theorem, and the idea is the following. You can look at the details in the book of Feller, but the idea is essentially the following, that if you want to compute the probability of this event, you should say for example, the probability of this event is related to the probability that is twice the probability that S of k is always on the positive semiplane by symmetry. So it's related to events such as this one, paths such as this one, where which are very similar to the paths that we use to prove the Ballot Theorem. Okay, the only difference is that we should add all the paths that end in any point on this axis. We should include these paths that end here, paths that end here, and paths that end everywhere. Okay. So what is the idea of the Ballot Theorem? Well, the idea of the Ballot Theorem is that you compute the number of paths that go from the origin to this point as the number of paths that go from essentially the reflected point here, so to the same point, okay? And essentially you say that the number of paths that go from the origin to this point B is equal to the number of paths that go from this point A to B minus the number of paths that go from the reflected point to B. Okay, so now you see that when you sum over all the positions of B, you can what you see is that so if you consider the number of paths that go from this point A to point B, these are exactly equal to the number of paths that go from A to a point that has to the next point, okay? Because this is a difference of two steps, and this is a difference of two steps. So when you sum over this axis here, so this term will cancel with the next one, okay? And so you are left only with the number of paths that go from this point to this point, to the first point, okay? So the point where S2n minus 1, because you start from 1, is equal to 1, okay? Because all the other terms cancel each other. And as a result of this, if you do the calculation, you get this remarkable result that the probability that from point when you start from 0, you never go back, you never return to the origin, is equal up to time to n, is equal to the probability that you return to the origin at time to n. Okay? Okay, so now how can you use this to find what is the probability that you have a first return at time to n? But the idea is that this is exactly equal to the probability that your first return is larger than 2n. Okay? And so this means that this probability can be written as the probability that the first return is larger than 2n minus 2 minus the probability that the first return is larger than 2n. Okay? And this is equal to u2n minus 2 minus u2n. Okay? So what is this? Well, let's do the calculation. So this is 2n minus 2, choose n minus 1, times 2 to the minus 2n plus 2, minus 2n, choose n, 2 to the minus 2n. Okay? So now let me rewrite this term here. This is so this term here is 2n minus 2 factorial divided by n minus 1 factorial squared times 2 to the minus 2n times 4. Okay? Now I can multiply and divide this by 2n minus 1 times 2n and divide by 2n minus 1 times 2n, and then multiply and divide by n squared. Okay, so if I take this n squared here, what I get is n factorial squared, and if I multiply this and this by this, I get 2n factorial. So I reproduce this factor here. Then what I'm left with is just these two terms here and this one here. So the n squared goes away with this. This 2 goes away with this 4, which becomes a 2. So I'm left with a 2n divided by 2n minus 1. Okay? So I can write this as 2n divided by 2n minus 1 times 2n n 2 to the minus 2n, and this is just so the final result is that this probability distribution F2n is equal to 1 over 2n minus 1 times 2n n to the minus 2n. Okay? So this is, so you see, by using this lemma, we can find an explicit expression of F2n. By the way, you can notice that if I sum from n equal to 0 to infinity F2n, I will get 1. Well, this you can get from this expression here, because, well, if you do this sum, you can start from n equal to 1. So this will be the sum from n equal to 1 to infinity, u to n minus 2 minus u to n. And you see that all the terms in this sum cancel each other, so you are just left with term u0, and this is equal to 1. So what this tells you is that the probability that the random walk will return to the origin sooner or later is equal to 1. So, so for sure, the random walk will return to the origin. So this is expressed by saying that the random walk is recurrent. So that this event, return to the origin, is a recurrent event that occurs with probability 1, and actually because it also occurs an infinite number of times, as we will see. Okay, so the last thing I want to mention is that about first returns is that we have already seen that this has this asymptotic behavior. So the asymptotic behavior of the first return probability is essentially when n goes to infinity, is given by 1 over 2 square root pi times n to the minus 3/2. So this probability goes to 0. You see that because this power is larger than 1, then this series converges. So but it goes to 0 very, very slowly, okay? And indeed, if you compute what is the expected value of the first return time, then what you find is that this is a series that behaves as n to the minus 1/2. So that it doesn't converge. So you get that the expected time to return to the origin is infinite. So for sure, the random walk will return to the origin. But so the expected time, the expected value of this time is infinite. And this is this might seem strange because in every realization of a random walk there will be a finite time, but where the random walk first returns to the origin, but the expected value diverges. Okay. Okay, so the last problem I want to discuss are the last visits to the origin. And so what is the last visit to the origin? So is the, now I'm considering a random walk of 2n steps, and that starts from the origin, and then I want to ask myself so if this is a random walk of steps 2n, I want to ask what is the last time that the random walk visited the origin, and let's call this 2k. Okay, and so I want to call f alpha 2n 2k the probability that last visit to O, to the origin, occurs at time 2k. Okay. Now I want to compute this probability, and again, because of this lemma, this becomes a remarkably easy task, because if this is going to be the first return to the origin, so the last visit to the origin, then first of all I should be at the origin at time 2k, okay, and then I should not visit the origin at any subsequent time. So S of nu should be different from 0 for any nu which is larger than 2k and less or equal to 2n. But you see that this probability is exactly equal to this when you replace the origin by this point. So this is exactly the probability that a random walk of 2n minus 2k steps never goes back to the origin. Okay? So, and by that lemma, we know that this probability is equal to the probability that a random walk goes back to the origin after 2n minus 2k steps. So this implies that this probability is equal to u 2k times u 2n minus 2k. Very simple result. Okay. So this law is called the so it is it's called the Ark Sign Law. It's the Ark Sign Law for last visits to the origin, and the reason why it is called the Ark Sign Law is because when n is very, very large, if you ask what is the probability that this last visit to the origin, what is this probability that that the last visit to the origin occurs before time 2n times x. Then this is clearly the integral, the sum over all k less than nx of this alpha 2k, 2n 2k. And now this for n large, you can approximate this probability this can be approximated for large n and large k as 1 over pi times 1 over square root k times 1 minus times n minus k. If both n and k are very large, then this is 1 over square root k, and this is 1 over square root of pi times n minus k. Okay, so this is okay. So if we rewrite these, if n and if n is very large, so this sum will be dominated by values of k which are of order n, and then I can use this approximation and write this as so use the variable x, which is k divided by n, and consider this sum over k as an integral in dk up to nx, say from 0 up to nx. And rewrite this as an integral from 0 to x of dx. So the dk is equal to n times dx. So then the probability is given by this. If I multiply by n, this gives me precisely 1 over pi times 1 over square root x times 1 minus x. Okay, so if you, this is called x prime. So now if you make a further change of variable, and you write z as a square root of x, then this integral becomes an integral of 2 over pi, the integral between 0 and square root z, square root, say, x, of dz over square root 1 minus z squared. Now if you make a last change of variable, yes, notice that the square root x, x is between 0 and 1, okay? So now if I make a last change of variable, say z is equal to the sine of theta, you see that dz is cos theta times d theta, but this is also cos theta, so this is just the integral in d theta, okay? So then you get that this is just 2 divided by pi times the arc sine of square root x, okay? So you get an approximation for the probability that L is less than 2n times x is for large n, this is given by the arc sign of the square root of x. This is why it is called the Ark Sign Law. So if you look at this result, this tells you that the probability that you get back for the last time to the origin at k is symmetric if you change k into n minus k. Okay, so if you plot this function here as a function of if you plot alpha to n to k as a function of k between 0 and n, then you find that you find a behavior of this type. So this tells you remarkable facts about fluctuation phenomena. So that contrary to what you would have expected, the most likely time when the random walk last visited the origin is either right at the beginning or right at the end. Okay, and so in particular, you see that the probability that it last visits the origin at the end is exactly equal to the probability that the last visit is at 0, okay, by this lambda. But this holds for all intermediate points. Okay, the least likely point where you expect the last visit is exactly at the midpoint. Okay, and so the other remarkable fact is that this same formula applies for other questions that you can ask. Say for example, you can ask, you can compute what is the fraction of this random walk, what is the fraction of time that this random walk spends on the positive side of the plane. And again, if you ask what is the probability that in a random walk of 2n steps, 2k of the edges are on the positive axis, you get exactly the same probability. So that tells you that a random walk most likely spends either all its time on the negative axis or all its time on the positive axis. And the least probable thing is that it spends half and half of its time on the positive and negative axis. And this behavior also applies, so this same law also applies if you want to consider what is the location of the maxima. So where do I expect to find, what is the probability that the maximum of a random walk will be attained at a certain point k. And again you find that the same law applies. So the random walk most likely attains its maximum right at the beginning or right at the end. And it is least likely that it attains its maximum at the middle. So quite contrary to the way I use to write random walks, where I said most of these things happened in the center.